physics in 2007, working with Peter Schneider. And she left a good impression here. So I somehow persuaded her to come to Caltech to graduate school. So I'm really sorry I've done that to you, but you survived. And she got a PhD in 2012 working with Chris Hirata, after which she went to be a postdoc at University of Pennsylvania, Kavli Fellow at Stanford, Spherex postdocs at Caltech and JPL, and then joined faculty at University of Arizona in 2018, where she's now a tenured associate professor of astronomy and physics. She is a very productive person. She published almost 200 refereed papers as author or co-author. She's very active in the leadership position. She was co-chair of the Science Committee for Dark Energy Survey and leads various similar groups for Rubin, for Roman, for Spherex, probably others. And she's been recognized as a Kavli Frontiers Fellow, Packard Fellow, Sloan Fellow, a whole bunch of other distinctions, which I can't remember. So she and Tim Euler are here for a sabbatical during this fall term, and I encourage you to go and talk to them anytime. So without further ado, Elisabeth.
Kind introduction, George. Thanks for introducing me to big data 20 years ago. As you heard, I'm here for a few months to primarily work on spherics. But as this is the center of the spherics universe, and many of you probably know more about it than I do in certain aspects, I thought I would talk about something else today. And that is some general aspects of doing cosmology with these very large surveys. So my title, Opportunities in a Systematics-Dominated Regime, is a mouthful and might sound not the most optimistic to some at first. But let me directly explain. I think this is a huge opportunity, especially for creative grad students, because the data is there, everyone can analyze it, but because it's dominated by systematics, including astrophysics, new ideas can really lead to analyses that will not happen in the key projects of the collaborations. And I'll give some examples of that throughout the talk today. So that's the basic idea. Now, let's see. Cosmology. All starts at bang, and then somehow we're here today, some 13 billion years later, much, much colder, much less dense universe. So about 13 billion years, huge energy scales to cover, and remarkably, by now we have this lambda CDM model that describes this vast range of scales surprisingly accurately. That is of order 10% level or better for many different observations. That's a huge success, but it's also really strange. To do all this, we require initial conditions created by inflation. We need dark matter and dark energy to then describe expansion history and growth of structure. And well, all of these are beyond the standard model of physics. So there's a lot that we still want to learn. Let me take you through a quick tour of how we want to better constrain these different properties. Our first line of attack is measuring the expansion history of the universe as directly as possible, and basically just measure the Friedmann equations, that scale factor as a function of time. For that, we measure distances as a function of redshift using two different tools, standard candles and standard rulers. Where last week's colloquium by David Schlegel about DESI largely talked about standard rulers. So in that case, we look at the angle subtended by a known scale. In this case, the imprint of the sound horizon at recombination on the galaxy density. And of course, we can measure that same scale on the cosmic microwave background. The interesting news now is if you compare this measurement at low redshift, as proved by DESI, to the cosmic microwave background, you can see that ratio indicated here by all the measurement points. And as insets, the actual measurement itself, that is this characteristic scale in the galaxy correlation function, it's a function of redshift, we find pretty excellent agreement. There's small deviations, and depending on what model you analyze it in, you either find that lambda CDM is a great model, or if you really open up parameter space, then you might be seeing hints for more interesting dark energy. So that's one line of attack, but this only probes the homogeneous expansion of the universe, which of course is just one part of the puzzle. The other line of attack is a growth of structure, where we can now gather a lot more of information. In a cartoon picture, we really want to understand at this point how configurations of quantum fluctuations end up in the late-time universe imprinted in the matter distribution. So through that process, we will learn something about the gravitational instability, in particular, the balance of gravity as we know it and dark energy pushing against it. And also, by the imprint of the initial conditions, what the particles and interactions and energy scales during inflation were. And then, of course, additional relativistic species or such at late times like neutrinos will also leave the imprint. Now, this is really quite a challenge for the lambda CDM model, as you can imagine, because we start out at the CMB time with relative density fluctuations of about 10 to the minus 5. And then we want to predict the evolution up to collapsed halos, so density contrast of over 200 in today's universe. So you can see that there's a lot going on. Now, to get the best possible constraints on that, of course, we need to think about how do we then best probe the distribution of matter and its growth history in the late universe. The textbook, likely you'll have seen someone work through growth of structure in terms of the density contrast. Maybe even the dark matter density contrast. That makes it easy, but of course also unobservable. So we need some more work. And let me just briefly walk you through here a few late-time tracers of that matter density field that we can exactly use then to pin down the balance of gravity and dark energy at late times. So instead of trying to work more with this unobservable density, we can look at halos, we can look at weak lensing, and the probes of the gas distribution in forms of the Zunyaev-Zadovich effects. So let me briefly introduce them in turn. Maybe the easiest to picture is halo-based probes. So in reality, typically, then we actually deal with galaxy-based probes, where for galaxies themselves, we often measure summary statistics of their spatial distribution, say the two-point correlation function, as I already showed in the BEO plot. But now we really want to understand not just one characteristic scale in it, but model the full shape and how also the amplitude grows as a function of time. For that, of course, we need to understand how galaxies relate to dark matter, also known as galaxy bias. Scary topic. Next up, clusters of galaxies. So probably our most direct probe of massive halos, which we can then hope to relate to the halo mass function, and with that, the distribution of peaks in the early universe. So complementary probe. First problem is finding a galaxy cluster. So for example, in this picture here, we have to decide which galaxies belong to it and where is its center. And then we have to figure out how to relate it to the halo mass that we can then relate to theory. And for that, additional surveys and multi-wavelength information may come in handy. Another at this dark universe is galaxy lensing. Let's start with a cartoon. We have some galaxies in the background. And if their light were propagated along straight lines, as shown by the blue lines there, we would see a bunch of galaxy shapes. Now, of course, there is a large-scale structure between us and those galaxies, and the tidal field distorts the shape of those background galaxies. And for example, they will then tend to align tangentially around a massive overdensity. This is a very weak effect. Per galaxy, talking about a signal noise of much less than 1. Meaning that we need to push to very faint galaxies, include as many as possible to increase our statistics. But of course, at that point, systematics come in. Measuring shapes at signal to noise of 15 or such, or fuzzy blobs, get challenging. And we then also need to estimate redshifts at low signal to noise. However, there are 3 different surveys doing this experiment at the moment. The dark energy survey, the kilodegree survey, and hypersuprime cam on Subaru. I would say we are in friendly competition, constantly cross-checking each other's analyses. And we all end up being skewed towards a lower amplitude of structure growth in the late-time universe compared to the cosmic microwave background. And while these are currently about 5% accuracy measurements, precision measurements, that precision will increase by an order of magnitude with LSST. So plenty to do. And since this sounds challenging, I'm happy to report that nature has also built in a cross-check. We have overlapping cosmic microwave background surveys. That same weak lensing effect, of course, also distorts the cosmic microwave background. And instead of galaxy shapes, we now look at a redistribution of the primary CMB anisotropies. So that is a completely different measurement of the same underlying physics, which means that we can use those two to cross-check against each other. And those two then, of course, probe the total matter density, dark matter, and whatever baryons do to them. The final player that I want to introduce in all these measurements are the Zonyar-Zeldovich effects. So this is generally inverse Compton scattering of CMB photons with some plasma that leads to spectral distortion. There's two main players here for large-scale structure studies. First of all, just the leading effect from astrophysical plasmas. That's the thermal SE effect, probing the total pressure of a cluster, for example. And then we can also detect, through a Doppler effect, the bulk motion of gas on the cosmic microwave background. That's the kinematic Zonyar-Zeldovich effect. And that allows us then to directly probe the electron distribution. From those combined, we can see where the electrons are, what the pressure is. So this really gives us a handle on feedback. One recent interesting measurement from DESI cross-Atacama Cosmology Telescope is that this kinematic Zonyar-Zeldovich effect measured in data, shown by red points, it must further extend it than we would expect from dark matter alone or from many hydro simulations. And on top here, I'm showing the illustrious simulation, which people in the past thought had way too extreme feedback based on group scale X-ray observations. But that strangely seems to be more in line with KSZ measurements, where, of course, I should mention that this type of measurement happens at a much lower mass scale than X-ray measurements. So that might already give us some clue of what could possibly be going on. So those are the measurements that I want to talk about today, the key observables that I want to talk about today. And let me just motivate why we want so many of them and why we want to keep pushing the science. I mean, we already know we have a beyond standard model, lambda CDM model to begin with. But even further, we are starting to see that model. There's currently primarily two tensions within that model. One is the Hubble tension, telling us that the expansion rate inferred from the early universe and locally disagree by more than 5 sigma. And we also find that the amplitude of structure growth that I already mentioned in weak lensing disagrees between the late universe, where this is a huge compilation of very different measurement techniques, basically the different observables that I just introduced, compared to the very early universe shown on top. This is not at the 5 sigma level by far yet, but it's still very interesting that so many different measurements across so many different observables all skew towards low structure formation amplitude at late times. Even more interesting, most models that have been proposed to cure one of these make the other tension worse. So it's really time to measure them precisely and see whether they manifest or go away as we achieve better mathematics control and better statistics. And then the ball is probably back in the theorist's court to produce more constrained models than have been flooding the archive in the last few years. So given this, probably want to get the most precise measurement on S8 as we can. So it's an obvious question then, how do we combine all these measurements? That's an easy task if your different measurements are independent. At that point, you can grab every experience result and multiply their likelihoods, as done here by the DESI calibration for combining CMB, the BAO measurement of expansion history, and supernova constraints on the expansion history, arriving at this nice combined result. Done. Now, if we want to measure structure growth, it becomes more complicated. because basically we're measuring the same underlying matter density field in multiple ways. So we have to be sure not to overcount information. Also, at this point, systematics are likely correlated, and we need to take account of that, because what we really need at the end is error bars that people will trust. So instead of multiplying likelihoods, we need to do let me take you through that, but in not too much detail. So what we're doing here is hierarchical inference, where at the end we want to get the posterior on some parameters of interest pi. And we do so by marginalizing over a bunch of nuisance parameters using our data likelihood. That's all pretty textbook, nothing fancy going on here. The question then really is, how do we fill the line? First question we of course have to ask, what's our science case? What particular parameters, lambda CDM or beyond lambda CDM, do we want to constrain? That then informs what data we can use based on what type of observations we can already model for that kind of parameter space. So just for one example, if somebody wants to constrain a fancy modified gravity model, where we only have paper and pencil predictions, then we probably don't want to include cluster counts or other highly nonlinear measurements here. Now that we've established our data vector that we measure, we also, of course, need a theory prediction for that. And that needs to be a consistent model across all scales and all probes, including the cosmology and nuisance parameters. That sounds kind of obvious. And in practice, this is mainly a question of diplomacy, because in the past, these were different working groups and surveys, or maybe working groups in different surveys, who don't necessarily talk to each other about their systematic parameterization. So in order not to end up with a Jacobian between SPT and DS parameterization, say, at each step of our MCMC, we need to get people to talk to each other. Then over here, of course, because this data is correlated, as I said, we'll need a covariance inscribing this correlation between all the different measurements. That then easily ends up being some massive integral over the meta 4-point function and such. And at this point, shout out to my thesis committee, who taught me that that's not good talk material. So if you want to know the details of that calculation, talk to me afterwards. And then comes the really interesting part, the nuisance parameters that we marginalize over, which means that we have to figure out what our systematics are and how to parameterize them. The main challenge here is that these will typically outnumber our cosmology parameters by far. So we need to really be strategic, figure out what parameterizations are needed, and how to prioritize all that. And then, of course, we need to trust our priors that we put on any of those models. So that's where external data and simulations may come in handy. And that's, again, part of the blueprint for some of this talk. Now, to do this in practice, we have a handy software package called Cosmology, which implements a likelihood framework for various correlated large scale structures. We currently have galaxies, weak lensing, CMB lensing, TSZ, currently expanding to KSZ. So basically all the players that are introduced are pretty much in there, including systematics parameterization at state of now. Importantly, it also implements that unspeakable covariance, for which this is still the only code in LSST and Rubin and in DS. And I know there's a software developer at ERP in Paris copying this code to Euclid standards to be used as a covariance code there as well. And then at the end, from that, we end up with a huge matrix like that, encoding how different of the observational probes are correlated so that we don't overcount information. That's, of course, all nice. In practice, this is one of the two analysis codes used by the Dark Energy Survey, and allowed us to really develop the methodology and say which models we can trust. It was also used in first joint analyses, including the first analysis that managed to combine cluster abundances, weak lensing, and galaxy clustering. More about that later. And it has been adapted as the inference framework survey cosmology team. Now, when I say it implements modeling for structure probes, let me give a brief flavor of that. First of all, we have a semi-empirical model, the halo model. So here we really start from the ground up, saying that all dark matter is partitioned into halos. And we have empirical measurements from simulations telling us about the density profile, halo mass function, halo bias, halo concentration, and so on. And then based on those building blocks, we can calculate statistics of like a galaxy clustering, saying that on small scales, all that matters is how traces are distributed within one halo. Scales, it matters how these dark matter halos themselves cluster. To fill that with life, we can then use something like a halo occupation distribution or some other prescription to assign galaxies or maybe TSZ or hot gas for TSZ studies to these halos, and then follow the same formalism in the end to calculate our observables. Of course, the goodness of this model really depends on how much you trust the different ingredients. Coming from the opposite side, that is from large scales, is the effective field theory approach, where we say, yes, halos are complicated, there's something going on small scales. If we smooth our fields, we don't need to understand that, and then can use basically all the scales between wherever we smooth and the horizon to just model everything perturbatively, saying that at this point we can use an effective fluid description, just accounting for some coupling from unknown small-scale physics on what happens on intermediate scales, similar to how you can do hydrodynamics without looking at each individual molecule. So that means that we decide what field we want to work with and write down an expansion about all possible terms. So for example, for density contrast, we expand in the linear matter density, keeping all terms allowed by the equivalence principle and by symmetry. So some of them vanish, and we don't need to talk about the detailed ingredients here at the moment. I just want to point out that we end up with quite a lot of free parameters. We can do the same trick for galaxy shapes, proceeds along the same lines, just becomes slightly more technical because now we're dealing with a spin-2 field. But in the end, we can then use the effective field theory calculus to evaluate 2-point or even higher point correlation functions. So at that point, we have a rigorous prescription for the scale dependence of these summary statistics that has a lot of free parameters. To fill that with life and really confront it with measurements then, we need some astrophysics to also include a time dependence, because we'll always have, say, different redshift bins or a measurement that's integrated along the line of sight. Generally, infusing some astronomy into this will help to reduce parameter space. So some quick example for bias expansion meets astronomy. One line of research that we are currently exploring in spherics is how we can maximize our FNL detection by using some astronomical information about galaxies. The key here is that the galaxy bias parameter relating galaxy overdensity to primordial fluctuations and to FNL has quite some rich astrophysics. We know that this deviates from universality expectations, basically saying that it matters that the halo mass function is the same in all environments, which means that we see some strong assembly biases with respect to phi and FNL, and basically giving a lot more richness to our FNL analysis. That means also that we have a new angle now on how to optimize these analyses, how we split galaxies into different bins. Just one quick example, trying this out on illustrious TNG. We found that if we split by observable proxies related to formation history, so say galaxy color or stellar mass at fixed halo mass, we can boost our significance detection, the significance of detecting FNL compared to the naive multi-tracer assignment saying we want the linear bias with respect to matter to be maximally different between two samples, which basically means we would split by total halo mass. But at that point, we run into the steepness of the halo mass and basically limit one of the two samples to shot noise, while here we have a much larger dynamic range. A bunch of other groups at the moment are also looking into how to reduce the dimensionality of the one-loop galaxy pi spectrum in the EFT of LSS, and generally find that, of course, putting better priors on bias parameters leads to better cosmology constraints. No surprise. But it will require to infuse some astronomy expertise to not end up in unphysical parts of model space. With that, let's get to my first real-world example of such a growth of structure analysis. That is the DES Year 3 weak lensing cross-galaxy clustering analysis. So briefly, in the context of various large-scale structure surveys, first of all, here by survey completion date, I show survey area indicated by these blue squares, and then also galaxy density as a proxy of survey depth in galaxies per square arc minute. So there were a bunch of surveys in the early 2000s that really demonstrated, yes, you can do weak lensing and galaxy clustering as a cosmological probe. Now we're in the era where we're analyzing 50 to a few 100 million galaxies with these 3 surveys in friendly competition. And that may sound like a lot, but really it's our boot camp for the next decade, where Euclid, Roman Space Telescope, and Rubin Observatory will bring us billions of galaxies of this type of observation. So here we want to probe the evolution of our invisible matter density field by looking at the distribution 2-point function of galaxies split in tomographic redshift bins and weak lensing. These 2 fields allow us then to calculate 3 different 2-point correlation functions. We can look at the clustering of galaxies with respect to each other. We can measure the cross-correlation between the galaxy position and the galaxy shape, which basically allows us to weigh the dark matter halos hosting these galaxies and constrain bias. And we can look at shape-shape correlations, cosmic shear. That's the high-level plan in detail. Apologies for the projector issues, but I was not going to talk through all these details anyway. That was our early Gantt chart for the DES Year 3 analysis. Let me show you what it ended up with, which basically means that we go from pixels of photons going into our telescope to cosmology constraints in 30 tightly coordinated papers. We have photons coming in, we detect galaxies, we do a bunch of calibrations, remove stars, do a bunch more calibrations to calibrate our photoses and weigh galaxies, say through galaxy-galaxy lensing, put in information from simulations and such, and out comes cosmology. Here's a slightly more scientific method of that. Obviously, I'm not going to cover 30 papers in this talk, but at that point, it was my job to make sure that they all interface properly. So if you want to talk about it sometime between now and mid-December, happy to. But since I'm here to talk about systematics, let me briefly tell you how simplistically we dealt with systematics in this big analysis. That is, try to get rid of as much complexity as possible. We have just 15 parameters for astrophysics to relate galaxy density and shapes to the distribution. We have another 13 parameters to describe observation systematics, which are in part fudge factors. And you can read the detailed list here if you want. My main point here is at the moment that this list is known to be incomplete. For example, we know there's baryons in the universe. Our systematics model does not account for this. So we deal with it by throwing data away. In practice, we throw out about half our signal to noise because we thought it was too difficult to model on the time scale that we had set ourselves to complete this analysis. So those are our known unaccounted for systematics. And then, of course, all these parameterizations here are our choice, not some deeper statement about the universe. I'm not saying by parameterizing linear bias as a step function of per redshift that that's what I really believe galaxies do. That's just my convenient choice. And I have to show that this is sufficient for our analysis. Off we go, do a few years of testing, and eventually come back to apply this to data. And at that point, we can, of course, split our data into 2 independent sets. That is cosmic shear, shape-shape correlations, and the 2 correlation functions involving galaxies, galaxy clustering and galaxy-galaxy lensing. After marginalizing over all the systematics and the remaining cosmology parameters, you see that these 2 contours agree pretty well. So we take this as a sign that our model was likely complete or sufficient. And we're allowed to combine to get these combined constraints. That's nice. We have a measurement of S8, but of course, that's not the main question. What people then really want to do is, so where do we stand with respect to the cosmic microwave background? So here we have our DS results repeated from the previous slide. This is the cosmic microwave background. And we find these to be at 1.5 sigma from the CMB. How do you call that? At the time that our papers came to my desk, one paper called it attention, another called it consistency. So I guess the answer is nothing to write home about yet. But as all the other large-scale structure surveys, we are skewed low relative to Planck. So in order to do better, we need better systematics control. We want to combine more probes and observe more galaxies. So let me take you through these in turn. First off, better systematics control. So now I can come back to my title and illustrate the opportunity space here. Here is a rogue DS reanalysis by Anthony Lewis. As a collaboration member, I would not have been allowed to produce this, but I'm really grateful. Because, well, here's our standard analysis, now shown in omega m and sigma 8, which is why it looks different. And then he did a bunch of bold choices. In this analysis, he fixes all nuisance parameters to the best fit values. Of course, we can't do that in a Bayesian analysis, but it indicates how much we could gain if we were able to constrain all systematics from external data. This contour then also includes all the signature noise that we gave up on. That looks super promising, but of course, that will come at the cost of additional systematics parameters. So this is even more overly optimistic. But still, it shows the direction. So let's talk about including information with better systematics control. The worked example from our group here is accounting for baryons in weak lensing analysis. As we know, galaxies have AGN, and they do their thing, and they will distribute matter, including outside galaxies. Here's just some snapshots from simulations showing you distribution of metals around galaxies in two different baryonic scenarios. One with AGN, one with just cooling in star formation. Clearly, a lot of material gets distributed, and in turn, halos will be less concentrated and puffier. That may then have an impact on weak lensing, which is why we threw out small-scale information originally. And this plot really illustrates how much signature noise we should throw out. So these are our tomographic shape-shape correlation functions. Because it's spin 2 field, we have two different correlation functions. Details don't matter on that at the moment. The main thing I want you to notice is that all these regions shown in gray are excluded from our analysis because of modeling complications. Our postdoc Hongjin Huang then went back and reanalyzed all the data, including the regions shown in gray, by including a model for baryonic effects. So to understand the possible range of baryonic effects, we looked at most of the hydro simulations on the market, hoping that simulators have not converged too much yet, and our universe will be somewhere within that envelope. What you see here is the suppression of the meta power spectrum in a hydro simulation relative to a gravity-only case. So that tells you basically how here, of course, in the center of halos, matter gets really concentrated in the central galaxy, and then halos get puffier, leading to the suppression. So we built a model from that broad range and apply it to our analysis. First of all, in orange here, I repeat the original analysis, as done with throwing out data, no baryon model. In green, we include all scales, but no baryon model. So that's the same problem as in the rogue plot. Don't do that. Green is not a cosmology analysis. In blue, then, we include our baryon model, marginalizing over baryons with very conservative priors. At that point, we're not biased, but we also don't gain much. But if we now put in even some minimal prior on baryons, saying that baryonic feedback in our universe is unlikely to be more extreme than illustrious, then we end up with this gray contour and have increased the constraining power by quite some amount, which would correspond to the next data release of DES, but we did it a few years earlier. Of course, a Bayesian analysis does not discriminate between parameters of interest and nuisance parameters. So we can, of course, then also turn this game around and ask, what does this tell us about baryons in the universe? So then we can plot the posterior from our measurements compared to various hydro simulations shown as dashed lines. And that seems plausible. So check mark, looks good. Next up, combine more probes. So here I briefly want to highlight the work by Chunhao To, then a grad student working with me, who extended the 3x2 point analysis of shear and galaxy clustering to now include also galaxy clusters in the form of the spatial overdensity of galaxy clusters and the number counts. So we developed a whole joint likelihood for that. And importantly, we use cluster lensing and cluster clustering only on large scales, which allows us to bypass small scale projection effects. So we don't really need to understand in detail whether a red galaxy belongs to our cluster or is a line of sight contaminant, which is something that plagues many other cluster analyses. And at the end, we obtain cosmological constraints that are consistent with other DS probes, which is remarkable because the other DS cluster analysis lost about half the matter in the universe, finding omega matter of 0.15 due to systematics that we still don't understand. So compared to just standard 3x2 point, we end up with these red contours, which again is a nice improvement. The interesting question now to ask is, why do we gain constraining power? Is it because we add another 2-point function, or because we add qualitatively different information? So we did this including and not including cluster abundances, finding that basically all this information here comes from including cluster abundances. That is, the shape of the halo mass function really provides qualitatively different information. If we can keep this up and accurately calibrate our mass-observer relation, we expect a similarly promising improvements with LSST, shown here in the dark energy equation of state parameter space. But that's a long road. Which brings me to, let's observe more galaxies. And there we really have exciting times ahead. We have all these large area surveys and nearly full sky surveys coming online that will provide rather complementary measurements. We have spectroscopy, low resolution spectroscopy, imaging in multi-bands, space-based imaging, and also space and near-infrared GRISM spectroscopy, and then CMB temperature and polarizations. So there's a lot you can do. Many people have called this decade the era of precision cosmology. And that will, of course, happen automatically. With bigger surveys, we'll get better statistics. So that will bring us precision automatically. Sorry, I'm out of range. So that will bring us precision automatically. However, if we apply the same analysis again, well, we might end up with wrong measurements. Because precision is not enough. Need is not just precision, but also accuracy. So that at the end, we're confident we are actually measuring the cosmology parameters of the universe. That will come at the cost of more complex analyses. And of course, the challenge that, unlike in this cartoon, the universe doesn't come with a bullseye where we know we're right. So we need to do some more work. And that's really where having multiple different probes and multiple surveys comes in handy. These different types of measurements are highly complementary, not just in the measurement techniques, but also in the astrophysics and the dependence on cosmology parameters. So that all of that provides huge opportunities. First of all, we can use the different measurements to do consistency checks between different probes and surveys, and with that, identify previously unknown systematics. We can do cross-correlations between different probes and surveys, and with that, then validate our systematics models more directly. And finally, we can combine different measurements to maximize constraining power. So let me take you through these in turn. Because we can plan for joint analysis before data arrives, that's that. And here I first want to talk about a new observable or new type of observation that we're currently developing, kinematic lensing. As I mentioned before, traditional weak lensing is a really challenging measurement because we want to find these small distortions in galaxy shapes, where shear is about a percent level effect, and the intrinsic ellipticity dispersion is about 25%. So that really means that we have a tiny signal to noise per galaxy, and with that, are really subject to many systematics. The basic idea then is that we want to measure shear on a per galaxy basis by including kinematic information. So again, let's start with a cartoon. We'll be using disk galaxies only throughout this measurement, where at that point then putting a slit along our galaxy helps us to say whether a galaxy is face on or inclined. So if we were in the rare case, we had a galaxy that appeared elliptic, had an ellipticity, but no rotation curve, we would directly know all this ellipticity here is due to shear, because it must be face on. In the intermediate case, where we see a rotation curve and some ellipticity, we can then put a prior from the Tully-Fisher relation to back out the inclination. And that allows us to get the unlensed shape, so that the difference between that and the observed shape will be our cosmic shear. Now, I've only talked about one of the two shear components. You can ask me about the second one afterwards. That's nice in a cartoon. So let's do it in practice. Out some of my collaborators went to get a spectra with Deimos targeting a galaxy cluster, so to compare to previous weak lensing observations. So specifically, we're using Abel 2261 and targeted a bunch of sources. Because we didn't know yet how to do this measurement. Afterwards, we realized that only a few of them had sufficient emission line signal-to-noise strengths to really measure kinematics. We also needed sufficient image signal-to-noise from previous data. And we needed to avoid galaxies with AGN activity or skylines. In the end, 3 galaxies were usable for our measurement, but it's a start. So this is then what weak lensing measurement with kinematics looks like. We have our image with a slit on it and our spectrum. Then we do a full forward modeling of image and spectrum with about 15 to 18 model parameters, including details of the galaxy profiles. From that full forward model fit at the spectrum level like this, we can of course extract a rotation curve and show that our model in that sense works pretty well. So here comes the shear measurement. These are our 3 galaxies as a function of or the tangential shear as a function of separation from the galaxy cluster center. And first of all, the good news is the error bars are as expected. So this technique performs as we hoped. Then we can compare to traditional weak lensing measurements shown here based on many thousand galaxies. And overall, that looks pretty good, except for this one outlier. At that point, we got unlucky again. Looking at detailed maps of the cluster, including strong lensing maps, we realized that, well, we're really at the position of one substructure here, apparently. 2 different strong lensing reconstructions disagree by that much on this particular location. So clearly, we got unlucky and something special is going on there. More details in the paper. But overall, this looks promising, and in particular, the error bars hold up to our theory streams. So with that, we're really looking forward to doing this with Roman Space Telescope, where we will already get from the community surveys overlapping imaging and GRISM spectroscopy. Based on our estimations, we expect sigma epsilon, so a shear measurement noise of about 0.03 to 0.04. So about an order of magnitude better than traditional weak lensing. And we've estimated the number, density of galaxies for ELG galaxies with sufficient signal to noise from Cosmos and candles. While we have about a factor of 10 fewer galaxies than traditional weak lensing available, the reduced shear measurement noise more than compensates for that. So here's our forecasts, how well traditional weak lensing and kinematic lensing will do on the same area in Roman. So assuming 2,000 square degrees for the imaging and spectroscopic survey of Roman. And that's about a factor 3.5 improvement in dark energy figure of merit. Good news is, these are observations that are already planned. so you don't have to rely on us theorists going to telescopes and get the observations right. We can just go and creatively reanalyze the data. And we're currently working towards the corresponding pipeline through a large Roman Whitefield science program, together with Eric Huff at JPL. All right, just one more example for the synergies between different services. I already told you how important baryons are for weak lensing. So let's bring in more information to do this automatically. So here we're looking at cross correlations between LSST and Simon's Observatory, including galaxies, galaxy shear, CMB lensing, and Sandowich effect, where our postdoc Xiao Fang went through the heroic, now extended covariance calculation, figuring out how all these different measurements are correlated. Because TSZ really is a one halo term effect. At that point, we really need to worry about gravitational mode coupling, and it's important to get this matrix right. But again, I want to bore you with those details. Let's just say that's the code now. Other people have started using it as well. And we use a toy model for the joint modeling of matter and pressure in halo model to explore how this might help us. And of course, we also throw in all the usual systematics. So forecasts that you see here are about 60, 70 dimensional MCMCs. No Fisher matrices were harmed. So we can look at what different combinations give us. The unsurprising answer, of course, is as we include more data, as we have higher signal to noise, we gain in constraining power. Nothing new there. So we go from galaxies plus weak lensing to include CMB lensing, to then also add in TSZ in cross correlation with the weak lensing and all the galaxies. And one of the interesting plots here again is looking at the systematics budget. Just some 2D projection of the constraints, showing you the fiducial analysis, how much we would improve if we could know everything about baryons and halos, and if we could fix all the systematics, so variant cosmology only. Of course, that black dash contour is impossible because there's a lot of fudge parameters in there. But of course, we can hope to make more progress on the halo properties and gas, including priors, say, from X-ray and such. Now, let's also plot the same data in a slightly different way to understand how self-calibration and the synergy between surveys really is helping us here. So instead of saying, yes, as we add more data, we get more signal to noise, and that, of course, boosts constraining power, let's take that part out. Let's assume we could do these measurements in a signal to noise matched case. And just for fun, I put everything here at the signal to noise of the total measurement. So that means that for conservative LSST only analysis, we would need an F-sky of about 1.2. Even I, as a theorist, understand that that's not possible. But that just shows you really how important it is to have these surveys overlap. So then as we start adding more and more information, you see that our constraining power per signal to noise increases. And that's exactly self-calibration or degeneracy breaking at work. So as we include small-scale information, we start to break some of the degeneracy between cosmology and halo properties. As we then add in CMB lensing, that really adds one particular source plane that helps to break a bunch of observational systematics degeneracies. So that gives us a gain in constraining power. If we add TSZ by itself only, we add more data, but a bunch of nuisance parameters. So we get a small dip. If we properly cross-correlate everything with everything, we gain more information. And then there's a huge bump possible if we better understand our halos. So that really shows how we will improve parameter constraints beyond the simple signal to noise expectation if we cross-correlate different surveys. And I have an ongoing project on SPT3G across DES, doing this in even more detail by including more information. But let me not talk about that today. I still want to talk about one data science aspect here, where after we've done all our planning, how having multiple probes and multiple surveys will come in really handy. And that is the idea of consistency tests and understanding our systematics. So we have all these different ways of trying to measure our parameters of interest. Let's first do them individually. and put them on the same plot. Constraining power is not optimal at that point, but that still provides a vital model check. If we see this, we say, yep, looks great. Probably our model is sufficient. Let's proceed. Confront that with this situation, we realize, no way, this model is insufficient. And we now need to go and work to figure out whether this is new physics or an unknown systematic. Of course, that's something that we've been starting to do for a while now. And in many cases, this has worked well. Produced analysis that the collaboration then says, yes, different measurements are good. You're allowed to combine and publish cosmology constraints. So some examples where this worked. But it can also show you that something really did not work. In our DES Year 3 analysis, one of the galaxy samples turned out to be more complicated than we thought. This is a red sequence-based galaxy selection using template fitting. And we think that there is some weird thing going on between the goodness of fit of the red sequence fit and dust or any kind of foreground extinction. So that leads to this huge mismatch between weak lensing and galaxy-based probes. But we haven't tracked it down in detail yet. We just know we have to work some more, and we should not trust the cosmology from combining these two. If we end up in a situation like that, question is how to proceed. Of course, ask, do the contours come together or grow further apart if we exclude some of the quasi-linear scales? It probably makes sense to ask how all this depends on galaxy cluster selection. And in some way, we could, of course, always follow up with more expensive measurements. Say we can calibrate ground-based lensing with space-based lensing. We can get additional spectroscopic redshifts to confirm photosees. We can get low scatter cluster mass proxies from X-ray surveys and such. But if it was not built in, each of this will be a huge effort and expensive. So the alternate route there is to plan ahead and build in a cross-correlation plan between different surveys. Just one example for this here is how we can use LSST and SO or CMB-S4 to provide a cross-check on our weak lensing shape measurements. Because again, these two weak lensing measurements probe the same underlying physics, just with wildly different measurements. And the black dashed line here is how well we need to control for, say, galaxy selection effects and such in LSST. Of course, understanding our galaxies gets more and more tricky at high redshift, which is where CMB lensing will come in as a cross-check. So these different colored lines here show how different combinations between LSST and SO or CMB-S4 will allow us to provide a check on weak lensing calibration from LSST. And if we've planned for a joint analysis, this comes in basically at just running a few chains and a few basic analysis, rather than going out to obtain additional measurements after a weird thing has happened. And that brings me to my conclusions. So data is coming, and it's fortunately for us coming in many different forms. Imaging, spectroscopy, and CMB, line intensity mapping in the future, and so on. Many of the individual cosmology constraints will be systematics limited, which of course is a challenge, but also an enormous opportunity for creative analysis. And for accurate systematics modeling, we probably need to calibrate, to collaborate all across astrophysics. And then finally, because the different surveys and probes enable precision and accurate cosmology by first allowing us to identify remaining systematic effects and then maximizing constraining power. But none of this will happen automatically. We really need to plan for these joint analyses through the tedious process of memorandum of understanding and such, and start to develop pipelines across surveys. Thank you.
Talk a little bit about your feedback.
About my
feedback, how you model effective feedback and how So we think we can do a good job with bilateral elements. So it can actually kind of trace how much matter is in halos outside. But we struggle to actually understand how to translate that into a feedback parameter that's useful. I'm curious, how do you model, what's the feedback parameter with those different lines, and how is that?
So at the moment, we are using a simple principal component decomposition of the different hydro simulations. So I showed you all these various suppressions of the matter power spectrum. At the moment, we built a principal component from that. And first principal component is at least at a level of DES sufficient. So we can then use that principal component strength to compare against the different hydro simulations. Otherwise, a halo model approach, really looking at how matter gets pushed out of halos and how that modulates the matter distribution in turn, is the other leading candidate at the moment. Happy to talk about that more. Yeah, including some of the codes that are out on GitHub from other teams. So the problem here is, I think that is really multiplicative degeneracy. So bringing in other cross correlations will not help. Designing galaxies where we think that one should be positive and one negative will at that point help. But unfortunately, there is, I'm not aware of a clear-cut path that bypasses simulations or semi-analytic models. Otherwise, we would be doing it already, I guess. Sure, that's basically a bread and butter ingredient in many parts of the pipeline by now. I think depending on where you start calling it, machine learning Gaussian processes have been around for a long time already. In recent years, there's been a lot of developments designing smarter and smarter emulators to really evaluate data vectors and then speed up likelihood inference across large parameter spaces. Our former postdoc, Vivian Miranda, has been leading some really interesting architectures on that. Of course, there's then also other approaches to directly use machine learning to predict the observables without that theory step in between, where to me it's still very much a question of how much we can really trust the training data at that point, given that we see that there are still problems sometimes reproducing observables with hydro simulations. We probably should not completely rely on that, but have some safeguards in a place where we can still do tests based on our physics understanding.
So let's thank our speaker again and remember.